thank you, Antonio, and thank you, Leon, and all of the organizers of this seminar. This is great. Also, thank you to Andrea. It's of course an honor to be sharing kind of this platform with him. And okay, so as Antonio said, so I'm going to talk about graph Laplacians, regularity theory, and these things. And then the way that the talk is structured. So so the title is this one. It's about regularity theory, but in fact, I'm only going to show regularity theory in the last 10 or 15 minutes. But then the first part of the talk will be kind of like a path to get there. So somehow I'm going to show you a bunch of results that they're going to be connected one to the other, and then they will culminate, or they will finish with this regularity theory. So please stay with me, and let's see where this takes us. Okay, so so then just kind of in more detail, the description of what I'm going to talk about. I have split this talk into these 4 acts. So in the first one, I'm going to give you like a very brief motivation, and show you some of the very basic and let's say first results on studying this graph Laplacians. Then I'll tell you a little bit about asymptotic spectral consistency of this graph Laplacians. I'll make sure that the setup is clear by that point. Then we're going to talk about quantitative convergence rates, first in the L2 sense, and then in the last part, I will talk about a stronger notion of convergence and also finer properties of this of the eigenvectors of these graph Laplacians. And so this is more or less the outline of the talk. And so okay, so then let's start by the beginning. Okay, so then the context where this graph Laplacians arise, at least for me, the motivation I have for my work is in data analysis. And in data analysis, we have data, and then we want to learn from data. Okay, and so there are at least 2 big frameworks or big paradigms of learning that are of interest. I mean, there are more than 2, but there are 2 that are very popular, and those are the unsupervised learning and supervised learning. So in unsupervised learning, the idea is that given a data set, you want to find a course structure, find clusters, and in the other setting, the supervised one, it's, well, you have the data, but you also have labels. Typically, these labels are given to you by an expert, this one being a doctor, an engineer, or an artist, for example. And the idea is to find a regression function so that whenever you get a new data point, you can label correctly. Okay, so there are these 2 frameworks that are out there in learning. Now, the idea is that, of course, like you want to use structure from the data to try to fulfill one of these tasks. And there is a framework for learning that is known as graph-based learning, where the idea is that you are going to inform your clusters or your regression function by basically a graph that you have on your data set. Okay, so the data set comes, we're going to imagine that it comes with a notion of similarity between data points. And then of course the idea is to use this similarity to fulfill those learning tasks. Okay. So then, for example, if we have this data set of handwritten numbers, the way we have to imagine them is really not just a bunch of images, but a priori we imagine that they are connected in a way like the one I'm illustrating here, so that there is already a graph. Okay, so I'm not going to discuss how you build a graph. That's of course very important, but that's not my focus on this talk. Okay, and then within these graph-based methods, there is perhaps another subfamily, very popular one, that basically relies on the construction of a graph Laplacian. Okay, so the idea is, well, you have a graph, what do you do with it? And so then you can say, well, if we want to summarize the geometry of this graph, one effective way of doing this, kind of inspired by spectral geometry, is to define this so-called graph Laplacian, which is just essentially you can interpret as a differential operator that takes functions on the graph into functions on the graph, and it's given by this formula over here. So then the idea is that if you are trying to use this graph Laplacian to fulfill one of these tasks of learning, well, you can do one of the things that I'm describing here. So for unsupervised learning, you can take your graph Laplacian, look at the first eigenvectors of this graph Laplacian. You find a threshold for how many eigenvectors you want. Again, that's perhaps an important question, but I'm not going to go into the details. But then once you have these first eigenvectors, you can use those eigenvectors to build an embedding. So you have originally your data set lives in principle in an abstract space. But once you compute these eigenvectors, you make a vector representation of these data points using these eigenvectors. And then once you have the eigenvectors, you can try to do a more traditional clustering procedure in the space, in the Euclidean space. Okay, so then the point here is the eigenvectors of the graph Laplacian are ultimately what gives you the clustering. In supervised learning, then you can basically incorporate also the information of labels that you have. So if you are trying to build a regression function, then typically you want to enforce some sort of regularity so that basically you don't overfit to the data. But then at the same time, you also want to be close enough to the observed labels. So then basically you can consider a minimization problem where you look at the graph Laplacian to regularize, and then you look at some sort of loss function to be faithful to the data set. Okay. So anyway, so this is kind of like things that you can do with graph Laplacians. You can do probably many more things, but this is just to give you an example of things that you can do in each of these learning settings. So now the question is, of course, in learning, there is one question that is always there, and not only in learning, but also in statistics as a discipline, and is the fact that, well, you do all this, you've tried to fulfill these learning tasks based on some training data, so some data that you observe. But of course, you want to use that training data to generalize, to be able to say what would happen if we observe data points that have not been observed yet. And one way that statisticians for centuries, I guess, have thought about this problem of generalization is, well, how about we study the statistical properties when we assume that our data sets or our graphs in this case are coming from some distribution, some ground truth distribution, some truth that we are hoping to learn from. So then the question here is, well, how can we do some statistics on these graph-based methodologies? Can we do statistics on eigenvectors of the graph Laplacian? Can we do statistics on solutions to problems like this one here? And so then for the rest of the talk, and this is something that people started doing in the early 2000s, well, the one possible model for how these graphs are being generated is the one that I'm presenting over here. So you imagine that data points are samples from some distribution. There is nothing super novel from a statistical point of view in that. And then, so here we're going to be imagining these are, okay, so these are IID points that are supported on some manifold. Okay, so this is a low dimensional object, perhaps. This is an assumption, a meta assumption, if you like. These are embedded in some big Euclidean space. And then the idea is that you build the edges in this graph by proximity. Proximity with respect to the ambient space, because at the end of the day, this is what you can do. The practitioner can only do that. So, okay, so if the data is in Euclidean space, the practitioner doesn't know what the manifold is, but it can compute distances on the ambient space. And so then depending on your interests and applications, you can consider other families of proximity graphs. It doesn't have to be what I described earlier as epsilon graph, where you connect points if they're within distance epsilon. You can consider other families, and for different purposes, it may be a wiser idea to build the graphs in a slightly different way. Okay, for the rest of the talk, I'm going to be focusing on this epsilon graphs, and then the manifold learning question, the statistical question or consistency question, is really to understand what happens when these graphs grow, while at the same time the scaling for how you're connecting the nodes in this graph goes to zero. Okay, so this last condition, the epsilon going to zero. So in this case, in this particular case, since we can build a graph at will, so since what we have is really the data points in Euclidean space, and we can choose epsilon in whatever way we want, this condition epsilon goes to zero is more kind of motivated from the point of view of you don't want your graph to be too dense so that later it's difficult to compute things with it. So somehow this is something that we can do here. In other settings where the graph is just given to us, then we don't have this choice. But here, in principle, one can do that. Okay, so then this manifold learning question, like, seeing what happens with this constructions as n goes to infinity, as I was saying earlier, this is a topic from the 2000s, the year 2000s. And you can see somehow even in the titles of these papers that there was this clear intention of trying to understand the large sample asymptotics of these objects. Okay, so perhaps I'm mentioning this one of Belkin and Yogi, which is perhaps the first one of this type of results. And then I have to say that in that time, in the first years, the main result was stated as I'm showing here. It's a pointwise type consistency result. Okay, and so by pointwise consistency, so you're trying to understand graph Laplacians, and then the first type of result that was out there had to do with what happens when you fix a function on your manifold. So you assume that you have your manifold, your data is supported in this manifold, you have a nice function supported in this manifold, and then you try to see if there is some sort of approximation of the Laplace-Beltrami operator, or some weighted version of the Laplace-Beltrami operator by this graph Laplacian. Okay, so here the f is fixed. You just want to see how this approximates, and most of the results were of this flavor. Okay, so here, well, okay, so this delta and epsilon is the graph Laplacian I was talking about earlier, perhaps appropriately rescaled to see an interesting limit, and then the limit is expected to be some sort of Laplace-Beltrami weighted by the density where these samples are sampled from, and maybe some constant that depends on the kernel that you use to build the graph. So okay, anyway, so maybe one thing to point out though is that, well, this result is quite interesting, and in fact we will see later on in the talk that are quite important. At this stage, it's not clear that this is saying anything about the consistency of the statistical procedures that we were using, because a pointwise result is not going to say anything about how the spectrum of the graph Laplacian behaves, or how solutions to variational problems related to the graph Laplacian behave. Okay, so this is an important result, but it doesn't fulfill, or it's not fully satisfactory in terms of explaining how the algorithms behave as n goes to infinity. Okay, so then what I'm going to show you now is a family of results that go in that direction. So how can we now analyze the variational problems or the spectrum of the graph Laplacian? And so I'm going to start giving you some results, starting with the more basic ones, and then gradually going towards I guess deeper understanding of what these things, how these things behave. Okay, so in other words, the consistency question, the first I'm going to consider is, as you take more data points, what can you say about the eigenvalues and eigenvectors of this graph Laplacian? And again, here, maybe we're thinking of epsilon goes to 0. I should mention that in 2007, perhaps the first result that tried to answer that question when keeping, say, the parameter epsilon fixed, so it's not going to 0. So this is this paper by Ulrich von Luxburg, Belkin, and Busquet, that they were the first ones that presented some results about what happens with the eigenvectors of graph Laplacians. But again, what I'm saying is that they consider this denser regime where the parameter epsilon does not go to 0. And then later with my PhD advisor, Diana Lipschitz, so we consider the case epsilon goes to 0. And this is what I'm going to talk about for a few minutes now. And so I'm going to give you right away the result that we had obtained at that stage. So basically what we have is if you take your parameter epsilon to scale in a certain way, so it's going to 0, but it's not going to 0 too fast. So there's some constraint on the dimensionality of the manifold where these points are supported. But then essentially, and of course, and there's some smoothness assumptions on your manifold, or in fact, okay, so in fact, our theorem was stated for domains in Euclidean space, but okay, so the same ideas apply for manifold. So as long as you have a smoothness, things like this, then essentially what you can show is that indeed with probability 1, you will have convergence of eigenvalues of the graph Laplacian. So this is the kth eigenvalue of the graph Laplacian, and then this is going to converge to the kth eigenvalue of the operator that appears right here. And there's also some convergence of eigenvectors, so at least up to subsequence. If you, I mean, perhaps you have multiplicity of eigenvectors, you always have like this sign kind of that you can flip around and so on. But up to subsequence, you can find convergence subsequences of eigenvectors of the graph Laplacian that converge to corresponding eigenvectors of this operator that appears over here. This convergence appears here is in some strange way that I'll describe in a moment. Okay, so but then the basic statement is that yes, you do have consistency as long as your graph doesn't become too sparse, let's say. So okay, so just to describe a little bit what were the techniques or ideas that we used to prove that type of result. So I guess here comes one simple observation, and is that these graph Laplacians are positive semi-definite matrices, and so the eigenvalues and the eigenvectors can be described in a variational form. So essentially, then trying to study convergence of the spectra is tantamount to basically studying minimizers and minima of weighted Dirichlet forms. So okay, so by weighted Dirichlet forms, what I mean is, well, this Laplacian will have some energy associated to it. So it's an energy like this one, properly scaled. And the Laplacian at the continuum level also has an associated Dirichlet energy that would look more or less like this. And so then to give you a hint of what is this TL2 space where we are comparing the eigenvectors of the graph Laplacian with the eigenvectors of the Laplace-Beltrami operator. So this is the way or the metric that we use to do this. So basically, the problem that one has is that you have functions that are defined on a point cloud, and you want to compare them to functions that in principle are defined on an entire manifold. And so then the way we try to match them, so to find kind of like a common ambient space where these things could be compared, was relied on ideas from optimal transport, essentially. So the idea is that if you have a function u on your data set and a function v on your manifold, you don't think of them as just functions, but you think of them as pairs where you also attach the measures, the corresponding measures associated to these objects. Okay, so what I mean by that is if you have the function defined on the data set, you're going to think of it as a pair where you also incorporate the empirical measure of your data set. And if you have the function defined on the manifold, you're not going to think of it on its own, but you're going to think of it as paired with the measure, the measure, for example, that you use to generate your data on your manifold. Okay, so really what we're doing is viewing these functions as pairs, where you first describe a measure on the manifold, and then you specify what is the function that is somehow built on the L2 space associated to that measure. And then on this space, you can define a metric, pretty much like I mean, it is essentially optimal transport, where you basically are going to be coupling the measures And as you couple the measures, you're going to see how far apart the measures are. This is what the distance between points is measuring. And also you're going to measure how different the functions are. This is what you're doing over here. Okay, so if you are interested more on this TL2 space and you want to see some applications to signal analysis, I recommend that you go to this paper of Matt Thorpe and collaborators, where they discuss these ideas in more detail. So anyway, so one thing that is interesting about this construction is that implicitly it is defining a sort of interpolation. So by interpolation, I mean you have a function on a point set and you want to extend it to the whole manifold so that now it becomes comparable to something that is defined on the whole manifold. And so then implicitly what you're doing is basically defining transport maps. So transport maps that associate points on the manifold with points on your data set. And then by composition with these transport maps, you are able to extend a function that is defined only on the data set to functions that are defined on the entire manifold. So this is not a Voronoi interpolation. This is not most of the typical ways of doing interpolation. This is an interpolation that is based on transport. And it has an interesting property that, in fact, we exploit, which is the fact that it preserves the mass, namely between empirical measure and the ground truth measure. And I'll show you in a few slides why that is useful. And so now just to kind of like wrap up the argument of how is that one can study variational problems on graphs, I mean, that involve the Dirichlet energy with the variational problems on the manifold that involve the Dirichlet energy in the continuum. I'm basically going to give you two ideas, and these two ideas are going to appear again and again in the rest of the talk. And basically the two ideas is, the first one is, well, you don't directly compare the discrete object, the graph object, with the continuum object, but rather you first compare to an intermediate object, namely a non-local energy. And then that's the part where you use the properties of this interpolation map. And once you have the comparison between the discrete and this non-local object, then you can go and study the non-local object. So how does the non-local object, what are the properties of this object, and how does it compare to the local Dirichlet energy in this particular case? Okay, so just to give you a hint of the ideas. So then this this is the intermediate object I was referring to. So here it's not a local energy, but it's not a discrete one. Here we're integrating instead of summing, and as well we have Laplacian that is not the summation. It's an integral. And so then basically the first idea for the proof, this discrete to non-local control, this interpolation idea, basically can be summarized in these two equalities here. So basically, if you start with some function on the point cloud on the data set, you can extend it to the whole manifold by composition with these transport maps. And then this basically, you will have a control that looks like this. So basically you have an isometry essentially, but then what is important is that you can control this non-local energy with some length scale epsilon tilde that is closely related to the one that you use to build a graph. Then there is some error term, and then above is dominated by the discrete energy. Okay, so it's important to notice that this is in a sense, it's a deterministic control. Okay, so it's a deterministic control, and it's also a quantitative control. So, I mean, and then here, just to give you an outline of how that proof works, and just to point at the specific property of the transport map that one uses. So basically, to make the comparison between this object here and this object here, one just basically follows this 4 lines. It's very simple. It's simple once you know that you should do this, but of course, it took a while to come to this construction. Anyway, so you have suppose that you start with on this left-hand side. You write its expression. You're integrating with respect to the empirical measure. Then you apply your measure preserving transformation. So now we're integrating with respect to mu, but now we're composing everything with the transport map. And so the key thing is that if this difference was not between t and x and t and y, but rather between x and y, the object that we would have here is really the non-local energy applied to the composition of U and Tn. But because we have Tnx and Tny, then, well, we cannot do that directly. But we can basically introduce some error term and compare this object over here by changing its, length scale, and then compare it to this guy in a pointwise manner. So for every x and y, you would have an inequality that looks like this. And then basically, well, the epsilon tilde is almost like epsilon, except that there is a correction term, but basically you get the control that you want. So then that was the first step, the discrete to non-local control. And then you say, okay, now you have this non-local object, what do you do with it? You have removed all the randomness, everything is now deterministic. So how can you, I mean, what do you do then? Then you go and check the literature on gamma convergence of these non-local energies, and then you realize that these non-local energies are converge nicely to basically the Dirichlet energy at the continuum that we want. Okay, so this is using the techniques of the Georgius gamma convergence, which as many of, I think, in the audience know, this is essentially sufficient and almost necessary conditions for convergence of minimizers of energies. And then basically, then if you put together these two ideas, the discrete to non-local and the analysis of the non-local, then basically the consequence is that this dn epsilon gamma convergence in TL2, this space that we introduce towards this continuum Dirichlet energy as n goes to infinity, provided that the error term is small enough, and basically it provided that this is true. And then you say, okay, well, I want to guarantee that this object is smaller than this one. Then the question becomes, well, how small that guy is in terms of n, the number of data points. And well, so from very interesting, nice results that go as far back as the 80s, essentially this object, this infinity transport distance scales in this way as a function of n. Okay, so then that's really what kind of how that result that I presented earlier works. And this is the first result that I wanted to show you. Okay, so now what I want to show you is there were many things in that analysis that I already showed that you could probably use not just to get an asymptotic consistency result, so n goes to infinity, but also actually get convergence rates. So to understand how the error scales with the number of data points and how it scales with the parameter epsilon. So that's what I'm going to show right now. So this is based on the three papers. The first one is by Burago and collaborators, and then two other works with my colleagues. Okay, so then the idea is, again, to use this two-step kind of analysis of, well, first understanding the discrete to non-local control. Now, one thing that I mentioned when I was discussing the asymptotic results is that actually you do have quantitative results there. At that stage, you already have quantitative results. Maybe they're not optimal, but you already have some. And then the next question is, well, what about the second part, the part where you are trying to take then the epsilon to 0, but n you imagine already as infinity. So then essentially the only thing that one really has to modify or be more careful about is the second step. Okay, so then the idea is that one can show that basically this Dirichlet energy, the one at the continuum, the local one, is controlled from above by the local one after you do some regularization. Okay, so here you start with a function v and you want to go down. Of course, if we don't do anything to that function, there is no hope to get an inequality like this. Typically, local energies are the ones that bound the non-local ones from above. But the point here is that there is an intermediate step, if you like. So there is some modification going on. And well, if you construct this modification in a smart enough way, then you can guarantee that the error term that appears in front is of order epsilon and not something different. But in principle, this idea you can try to modify, and you will get an inequality of this flavor, which is quantitative, and there is nothing random in it. And once you put kind of like the two ideas, so the discrete to non-local control and this kind of a non-local analysis together, then you get an inequality of this type, where basically what we have is now you have a quantitative estimate of how the eigenvalues, the discrete ones, how they compare to the continuum ones, let's say. And also you would have some quantitative convergence rates for the discrete eigenvectors with the continuum eigenfunctions. Okay, so they depend explicitly on the mode that we're looking at, and also on these quantities that we had talked about before. And so this is basically the one way to obtain convergence rates. One interesting thing about this statements here is that if you use the expression on the right-hand side, you use Weil's formula for the growth of the eigenvalues, you basically can explain, or at least quantify, when this kind of plateauing starts happening for the graph Laplacian. Okay, so here I'm imagining a sphere, and I'm imagining a graph on the sphere, and I'm basically plotting how the eigenvalues of these two things, the Laplace Beltrami on the sphere and the eigenvalues of the graph Laplacian behave. And then you're going to see a behavior like this. So of course, if we want to make this uniform on all k, that's not going to happen. It's not going to happen because the error here appears, and depends explicitly on the mode that you're looking at. And so of course, if we want the left-hand side to be small, epsilon times whatever has to be small enough. So those estimates allow you to see a little bit of that. Now, one side remark is that similar ideas to what I presented earlier can be done to not just for the spectrum problem, but also for Chigurh-Cutts. And if you do this construction and combine with the quantitative isoperimetric inequalities that have been developed in the past 10 years or so, then you can get also convergence rates for Chigurh-Cutts on data clouds when your manifold is generic enough. Anyways, that's a side remark. Now let me just say one word on how those convergence rates that I presented actually can be improved. But somehow the results that I presented are kind of like needed a priori. Okay, so what I'm going to say now, describe very briefly, is once you have some convergence rates, now you can improve them. And so then the trick is more or less like this. So if you have a discrete or graph eigenvector, you have a continuum eigenvector, suppose that both of them are normalized, you can basically follow like a very simple computation where you are basically just trying to understand the difference between the continuum eigenvalues and the discrete eigenvalues. And so just like following basic properties of this these Laplacians, at the end one gets to an inequality that looks something like that. And then the thing is that this object here now becomes like what we had at the beginning when I talked to you about the pointwise consistency. So V here is a fixed eigenfunction at the continuum level, smooth, if we assume that the manifold is smooth. And if we beforehand, we already know that the discrete eigenvector U and the discrete eigenvector and the continuum eigenvector V are kind of converging one to the other, we can then treat this guy, this denominator here, as a constant, essentially. And so then basically the left-hand side, the difference of the eigenvalues, is dominated by essentially the pointwise convergence rate that one had at the beginning. So the point is that with a priori estimates, to know that this is not going to zero, then one can actually upgrade the convergence of the eigenvalues to the pointwise convergence rates, which actually are much faster. And in particular, they look something like this. So you basically get, as long as epsilon is not too small, there is kind of like a different scaling that appears there. This comes from the pointwise results, but then basically the convergence of the eigenvalues and the convergence of the eigenvectors happen linearly in epsilon, and you can quantify with very high probability how those things behave. Okay, so that's kind of the summary of the L2 convergence rates. And in the last minutes of the talk, I really want to talk about the title of the talk. So the topic that gives the title to the talk, which is, okay, so you have all these L2 estimates and, you know, these convergence rates and quantitative convergence rates, but what can we say about the eigenvectors as functions? In particular, are they regular enough? And is there a stronger sense in which one can show the convergence of the graph eigenvectors towards the continuum eigenvectors? So then, I mean, just a simple plot. So here, you know, this was a function that is kind of a linear combination of a bunch of eigenvectors of the graph Laplacian, a few of the eigenvectors actually. And then basically you want to see how regular that function is. And okay, here this is a piecewise constant interpolation. So of course, it doesn't necessarily look super regular, but still you see that there is a lot of a structure there. There may be hope that in fact these functions are regular in some sense. So in joint work with Jeff Calder and Marta Lewicka, we give a sense of that regularity. We give concrete sense of the regularity that we were observing in those pictures. So our theorem basically says the following. It's a global Lipschitz almost Lipschitz estimate, let's say. So it basically says that as long as you know the epsilon that you're using to build your graph is not too small, so similar to the pointwise scaling, then with very high probability, every function defined on the graph, every single function defined on the graph will satisfy a bound that looks like this. Okay, so basically it's saying that the difference, if you look at the function evaluated at some point xi, and then you look at how does the function behave on a point xj, presumably nearby, well then basically that depends on the distance between the points, that would be a Lipschitz estimate, and then some correction, this plus epsilon, which presumably comes from the fact that you're looking at this non-local objects, let's say. Okay, and then the Lipschitz constant will depend on the Laplacian of this U tilde that you're considering, so a uniform control on that object, and also it will depend also on the uniform norm of this function U that you started with. Okay, so this is a result that holds for every U tilde. And I'm just gonna, first I'm gonna tell you how to use that, and then I'll give you a hint of how is that one can obtain such a result. So then basically, let's start with the regularity of eigenvectors. How can you use that general identity or inequality to show a regularity of eigenvectors? So this is the general inequality. So for every U tilde that this holds, and then you can say, well, just take U tilde to be a normalized eigenvector of the graph Laplacian. Then you just plug in. So you just plug in U tilde, and well, this guy is again U tilde times the eigenvalue. This is what we have here. Now you need to control the L infinity norm of U, but actually it's interesting because already from here, and this is a simple computation when one sits down and sees exactly what this means, actually you could say, well, don't you need an L infinity control on U to use it for something? But in fact, from this inequality already it follows that you can get L infinity control on U from, for example, L1 control on U or L2. And if you were assuming that L2 norm of U was 1, then essentially you have a control on the supremum of U in terms of the eigenvalue that you're looking at. So then the point is that as long as you can take, I mean, as long as the epsilon that you're considering is small enough with respect to the mode that you're looking at, the eigenvalue you're looking at, then basically what it reads is that you basically have that eigenvectors are almost Lipschitz functions with constant that depends on the eigenvalue that you're looking at. And I say almost again because there is this epsilon correction term, which presumably you cannot remove. So then the bottom line is that essentially you have this almost Lipschitz property of the function U. Okay, so that's regularity. Now let's look at the second part that you can use from this general result. So the second part is, well, we talked about L2 convergence rates of eigenvectors towards, of graph eigenvectors towards continuum eigenvectors or eigenfunctions. So can we do better? Can we do better than that? Okay, so then the idea is, yes, you have, again, you have a general inequality. So you can take any function that you want. So how about you take the graph Laplacian eigenvector, you subtract a continuum Laplacian eigenfunction. You treat that eigenfunction as you restrict it to the points. Of course, we're assuming smoothness on the manifold so that that operation makes sense. But then the idea is, well, these are eigenvectors for each of the Laplacians. Then one can say, okay, so if we want to use this general inequality, we need to estimate the Laplacian of that function U tilde. And then you see, well, you just decompose into terms. Then you recognize, well, this is the function itself. Here is a difference of eigenvalues that we know we can control very well. Here is a difference between graph Laplacian of a smooth function and its continuum Laplacian, which we can control very well because we already have this pointwise estimates. And then the point is that in a very similar way as in the previous, I mean, it's in the regularity for eigenvectors, one can basically get control on the L infinity norm of the difference between U and V in terms of the L2 difference between U and V. And remember, we had beforehand, we had this L2 convergence rates of how discrete approaches continuum. So the bottom line is when you put everything together is that now one can say how the almost Lipschitz constant between U minus V behaves in terms of the L2 control of U and V. So in other words, since we already have this, we have very quantitative way of characterizing the right-hand side, then we also have very nice quantitative way of characterizing the left-hand side. Okay, so then basically, that's kind of how you put together the L2 convergence rates with this new kind of machinery of regularity, say, to obtain stronger notions of convergence, to obtain regularity of the eigenvectors, and hopefully in the future more interesting aspects of these graph Laplacians. Okay, so I I know I'm running a little bit late, so I just need 2 minutes to give you a very brief sense of how we prove this general result that we were that I was discussing. So this general regularity result. So essentially, we maintain this kind of a structure of the proof where you try to analyze some sort of discrete to non-local control. Here is going to look a little bit different, maybe with a different interpolator. And then there is going to be a second step, if you like, where you do some non-local analysis. Okay, so then for the discrete to non-local control, there is a new interpolation. So it's not anymore in terms of transport maps, but it's a little bit more direct. This object is actually related to the graph Laplacian, but okay, I don't have time to discuss that. But the point is that the estimates that you would like to get for graph Laplacian, you can kind of move towards getting estimates for the non-local Laplacian. Okay, so then these 3 inequalities that appear here is essentially what allows you to move from, well, let's not analyze the discrete Laplacian directly, but rather let's just try to analyze the non-local Laplacian first. Okay, so this is somehow what this is saying. And then basically the second step would be to obtain the regularity for these non-local objects. Okay, so then basically you almost don't notice the difference. The only thing that is changing here between this and what I presented for the graph Laplacian is that now V in principle is defined on the whole manifold, and this Laplacian epsilon is the non-local Laplacian. So it's almost the same quantity, same kind of inequality. But then the point is that the step 1 allows us to say, okay, if we can show this for the non-local Laplacian, then you can put the 2 things together and get the theorem. All right, so then 1 extra minute just to say that how do we get this non-local Laplacian global regularity? So then basically we use coupling methods, so coupling of random walks. So to study regularity, there has been, since the 90s at least, there's been these ideas from probability theory that were basically by tracking random walks and random walks that are coupled, actually, you can do a smart analysis, use martingale methods, and ultimately obtain regularity from probabilistic estimates of these random walks. So here we follow a little bit of that literature. And then ultimately we get this type of result. So, okay, so then I think I'm running out of time. So let me just say then, just to summarize, so I presented this kind of path between the early results on pointwise consistency of graph Laplacians all the way to these regularity estimates, and in between there were these L2 convergence rates. What I would like to stress is that perhaps one could have done the last part without the first one. I'm not sure, but at least the way I found this topic and this object was actually in sequential form. So in fact, and this is what I wanted to stress in the talk, that this result somehow kind of build up and you can reuse them once again in later stages. There are a lot of, I think, exciting things that one can do with these results. One can also ask about higher regularity and things like this. But I think at this point, there is also, of course, a lot of, I mean, I guess, excitement. I don't know how much that is concrete. But anyway, so I think this is all I wanted to say. Thank you for your attention, and thank you for my funders and my collaborators throughout these years.